In this week's lectures, we've been looking at the distribution of the OLS estimator. We've been using the Gauss-Markov assumptions to derive a statistical distribution for the slope coefficient in the OLS regression. And once we've got that, we can use this distribution to construct hypothesis tests about these coefficients. The second part of the lectures, we've been looking at the goodness of fit of our regression equation. In other words, how well does our regression fit the data that we're dealing with. In last week's lecture, we showed that we could write the slope coefficient from the least squares model as beta hat equals beta plus the sum of xi minus x bar ui divided by the sum of xi minus x bar squared. Now, what's useful about this is it shows that the least squares slope coefficient is a linear combination of the random errors from the original equation. And if we can go on and make the assumption that these random errors follow a normal distribution, it follows that the least squares slope coefficient also follows a normal distribution. The reason for that is that any linear combination of normal random variables is itself normally distributed. Given this, we can derive the distribution of the least squares slope coefficient by deriving its mean and its variance. And we showed last week that we can derive its mean very straightforwardly. If we take expectations, then using Gauss-Markov assumption 4 and Gauss-Markov assumption 1, we can show that the expected value of beta hat equals beta. This week we took a look at the variance. Now, the variance is defined as the expected value of beta hat minus its expected value squared. And to derive the variance, we need to make use of the other Gauss-Markov assumptions, Gauss-Markov 2, that the errors are independent, and Gauss-Markov 3, that the errors have constant variance. And if we do that, we find that the variance of beta hat, which is equal to the expected value of the sum of xi minus x bar ui divided by the sum of xi minus x bar squared, all squared, can be derived as sigma squared, and that's the variance of the random errors u, divided by the sum of xi minus x bar squared. What's interesting about this is that as the sample size gets larger, the expression on the denominator will get larger as well. We'll have the sum of xi minus x bar squared will become very large as the number of observations becomes very large. As a result, the variance will shrink. What that means is that when we add more data, we get more and more precise estimates. The variance of our estimator collapses towards zero as the sample size becomes infinitely large. Of course, in practice we don't have the luxury of infinite samples, but nevertheless this is an interesting result because it establishes the common sense conclusion that more data is always better than less data. Now, we've established that under the assumption that the errors are normally distributed, the slope coefficient beta hat is also normally distributed, and we've now defined its mean beta and its variance sigma squared of the sum of xi minus x bar squared. We can further transform this to make it useful for hypothesis testing by using the Z transformation. So we can show that beta hat minus beta over sigma divided by root sum xi minus x bar squared will follow a standard normal distribution with mean 0 and variance 1. If we knew the population variance of the errors, the sigma squared, then we could use this directly. Unfortunately, in most circumstances we don't know this, so we substitute an estimator sigma hat for the error variance or the error standard deviation, and we show that this expression here, beta hat minus beta over sigma hat divided by root sum xi minus x bar squared is or follows a t-distribution with n minus 2 degrees of freedom. In the second part of this week's lectures, we looked at the analysis of the goodness of fit of a regression. To do this, we first of all defined the residual sum of squares as the sum of the squared differences between the actual y values and the fitted values from our regression equation. We compare that with the total sum of squares, which is the sum of the squared deviations of y from its arithmetic mean. One of the basic statistics we can use to analyse the goodness of fit is the R squared, or coefficient of determination of the regression, which we define as being equal to 1 minus the ratio of the residual sum of squares to the total sum of squares. We showed in the lectures that r squared must lie between 0 and 1, with 0 indicating no relationship and 1 indicating a perfect fit for the regression. Other useful statistics are the F statistic, which is a test for the joint significance of any right-hand side regressors. This will be more useful when we come to multivariate analysis. The F statistic is defined as the ratio of the difference between the total sum of squares and the residual sum of squares, which we can think of as the explained sum of squares from the regression, divided by its degrees of freedom, 1, and then dividing that by the residual sum of squares divided by its degrees of freedom, n minus 2. And we can show that that follows an F distribution with 1 and n minus 2 degrees of freedom. And we can use this as a basic formal test for the joint significance of right-hand side regressors. Finally, we look at the standard error of the regression, sigma hat, which we define as being equal to the square root of the residual sum of squares divided by its degrees of freedom, n minus 2. We can think of this as a measure of the standard deviation of the residuals. This is more useful when we're comparing the fits of one model with another model. These three statistics are actually quite closely related. We can show, for example, that we can write the F statistic as r squared over 1 minus r squared times n minus 2 divided by 1. And we can also show that we can write the standard error of the regression, sigma hat, as the square root of 1 minus r squared times sigma squared y, where sigma squared y is a measure of the variance of the endogenous variable y. It's the total sum of squares divided by n minus 2. Finally, we took a look at how we could use some of these statistics in an actual regression equation. The equation here is a regression of the growth rate of investment spending on a constant and the growth rate of GDP. And we've estimated the slope coefficient at 1.93. Now, using these statistics we've derived, we can do a formal statistical test for whether or not this is significantly different from 0. And to do that, we obtain the t ratio as the ratio of the coefficient to its standard error. That gives us a t ratio of 7.66. If we compare that with the critical values, we'll see that that is in fact very statistically significant. We can also assess the goodness of fit of the regression by looking at statistics like the r squared, which is 0.51, which indicates that our model is explaining about half the variation in the particular series we're interested in. The F statistic is a formal test for the significance of the right-hand side regressors, but in this case, because there's only one regressor, it's again a test for the significance of the slope coefficients. In fact, we can show that the F statistic is actually in this case the square of the t statistic, though of course this relationship doesn't survive when we move to multivariate regressions. Finally, we can get a measure of the goodness of fit by looking at the standard error of the regression. We see here that this is actually quite small, 0.03, but this is a measure of the standard deviation of the residuals, and so it's going to depend upon the actual nature of the data that we're dealing with.